Diehl. I did my research on the pounding effects on seismically isolated structures in the Department of Civil Engineering here, and I work with Dr. Gilberto Mosquera. So today I'm just going to talk about, I'm going to go over what base isolation is, what base isolators are, and what pounding is. I'm going to talk about our experiment, the design of it, what we plan on doing over in the lab. I'm going to discuss a numerical analysis I conducted on a computer simulation on a 3-story building, and then I'm basically going to talk about what we hope to gather from this experiment. So base isolators, what they do is they separate the substructure from the superstructure, as you can see in this picture here. There's like this kind of layer of flexibility in between here that dissipates energy from earthquakes. So in addition to energy dissipation, what they do is they change the fundamental frequency of the structure, which is important, especially in medium height buildings, because the fundamental frequency of these buildings typically falls within the range of earthquake excitation frequency, which can lead to a phenomenon called resonance, which is basically when when a body is excited at the rate at which its fundamental frequency, which leads to amplified vibrations, which can cause destruction. As you can see here, it typically leads to a lot of collapse during earthquakes. These are two of the different types of isolators we're going to be testing in the lab. The first one on top is called the low damping rubber bearing. It's basically just two alternating layers of vulcanized rubber and steel shims in between two steel plates. It provides a lot of horizontal flexibility. The second is friction pendulums. It does the same thing essentially, just a different method of doing so. It's a concave disc and housing plate in this articulated slider here. It's coated with a friction layer. So basically the structure is free to move on top of these isolators, separate from the motion of the foundation of the structure. Pounding is a phenomenon that occurs typically between adjacent buildings during earthquakes when they collide into one another. We're going to be looking at moat wall pounding, which is a little bit different. For base isolated structures, there's something called a moat wall that goes around the bottom of the structure just to give it some freedom to move during earthquakes. One of the concerns in the event of pounding could be the whiplash effect, where the bottom of the structure suddenly has to stop due to impact, but the top wants to keep going due to its inertia. So we're trying to determine the effects of that, and we also want, basically the big question we're trying to find out is what this gap size has to be here in order to have an ideal barrier between the structure and the moat wall. So for our approach, like I said, we're going to be simulating moat wall pounding on a seismically isolated structure using the earthquake tables over in Ketter Hall. Our structural model is a 3-story steel moment resisting and gravity frame. To simulate the pounding, we're attaching concrete blocks to the base of the structure, and they will collide with concrete boxes that are filled with soil, which simulate the moat wall, and the boxes will be placed at varying distances to simulate different gap sizes and different impact velocities. This is a AutoCAD drawing of our structure done by Armin over here. On the outside, you can see the moment resisting frame. On the inside is the gravity frame. Here are the concrete boxes. You can see the soil inside it. Here's the concrete blocks, and like I said, they're going to slam into each other to create pounding. Here are the base isolators. on either side of the structure, and on the bottom are what's called load cells. What they do is they essentially just take measurements of the forces and moments found within the isolators just to see what kind of effects, what kind of stresses they're going through throughout the experiment. So for a numerical analysis I conducted, we ran a computer simulation on 20 different ground motions on a 3-story building, like I said, and the point of this was to try and determine if there is a relationship between the velocity of the base of the ground floor of the building and the displacement of the ground floor. So the procedure was we basically just found the maximum velocity of each ground motion in both the x and y directions at 3 different displacements. The first was the smallest maximum displacement. So every ground motion initiated at least this displacement in the structure. The second was the average maximum displacement in either direction for each ground motion, and the third was the projected maximum displacement using the equation you see here. It was projected before we ran the simulation, and as you will see right now, the actual average was a lot different than the projected average was, which will come into account when we run the test. Here are the different graphs of the results of the velocity versus displacement. On the top is the x direction. SM stands for smallest displacement, DM is the average displacement, and PM was the projected displacement. And like I said, in both directions, the actual average displacement was significantly less than the projected displacement. Which is one of the conclusions we came to. Less than half of all the ground motions in either directions reach the projected maximum displacement. The same can be said for the actual average displacement. Most of the maximum displacements fell below the range of the projected and average maximums. And as you can see from the graph, there was, as the displacement increased, the velocity tended to decrease as well, which was kind of what we expected. So far all we've done is this numerical analysis. We haven't begun testing the actual structure yet. We've begun construction on it a couple weeks ago. The whole point of the experiment is to attempt to understand the effects of pounding on seismically isolated structures, which there hasn't been much done as of yet to determine this. Only numerical analysis has been conducted so far. And like I said, the whole point is to determine what the gap size should be between the structure and the mold wall. Here are my references. And that's all I got. You guys have any questions?
How big is the simulation 3-story building that you're putting in Keter? I guess, how big is it? Well, are you actually putting a 3-story building?
I don't think so. It's a model, right? It's gonna be shorter. What's that? It's a 1/4 model. So
1/4? Oh, cool.
It won't be quite as tall as 3
Still cool.
but it'll still be big.
Mm-hmm.
Any other questions?
Are you so you said there were 2 types of big isolators?
Yeah.
Do you use both of them, or compare one versus the other?
We're using both. Like, we're not
Okay.
using them both in conjunction, but we are.
Okay.
Yeah.
Okay. And you haven't done it. You haven't built the actual structure.
We just started construction a couple weeks ago.
Okay. And you said one of the points is way below the average displacement.
Yeah.
Why? Why was that?
Wait, what do you mean?
Like, there was a curve showing that small displacement, average displacement, and projected displacement, and I was wondering why was it below? Why was the projected displacement below the average displacement?
The projected displacement was higher than
Was
the
higher,
average
right.
displacement.
Okay, so why? Oh, okay, so. Never mind.
Okay. Any other questions?
And are you actually building this yourself, or do you guys have another team that actually does build?
We're building it ourselves.
Are there any projections for how long it would take to go from testing stage to actually implementation in like earthquake places like California?
Well, seismic isolators, they're already used throughout the world where earthquakes do commonly occur. The point of this experiment is simply to determine the effects of pounding, like on seismically isolated buildings. They're already, especially in California and places like Japan where earthquakes frequently occur, there are seismic isolators in place in a lot of structures already. Like a place like Buffalo, you're not really going to find them because you don't really need them. But yeah, they are in effect.
Do you have like a general example of a seismically isolated building?
What do you mean, like?
What exactly are they?
Let me go back. They're basically, I mean, you're not going to find them here in Buffalo, like I said. There are bridges in California. There's a lot of municipal buildings that are seismically isolated. And like I said, it's just a regular building, but in between the foundation and the actual, typically they're found right below the basement of a building. There's this layer of isolators which provide horizontal flexibility.
In general, how much does it cost?
Honestly, I'm not sure. I know it's not. I know a lot of buildings, they're retrofitted, like, you know, the structure's already built and they go in after that, and then the isolators are applied. Like, as far as the cost though, I'm honestly not too sure. I can find out for you if you'd like.
Oh, wait, so you can build a building and then put, like years after you, then you can put it
Yeah,
underneath?
it's actually pretty common.
Wow.
Any other questions? Okay. Cool. Thank you.